Good morning. I hope you guys are doing well today. Or it might be good afternoon when you're watching this. I'm not sure. This is going to be a two-part video over the polar form of complex numbers. Complex numbers was something that we saw in Algebra 2. We'll do a small review on here in just a little bit. And what I'm going to do is I'm wanting to get it to something that is called polar form. Now, before we start this video and some of the next videos over the next couple of weeks, I want you I love this quote by Leopold Kronecker. And he said, God made the integers. All else is the work of man. Just keep that in mind as we go through some of these next few videos coming up. I'm not trying to scare you with that, but just keep that in mind. Okay, so we have all these complex numbers, and a complex number is going to be a number that is expressed in the form a plus bi. And we like to use the variable z to represent a complex number, where a is going to be my real part, and then the bi is my imaginary part. Oh, wow. Imaginary. Here we go. Imaginary part. So a lot of times whenever we solved a quadratic back in pre-calc A, if it didn't come out to something that factored, we got imaginary numbers. We'd get 3 plus 2i, or 3, or maybe negative 7 minus the square root of 2i. And so all of those fit into this idea of a complex number. Okay, now, we can actually get into graphing these. I took a whole year in my master's working with these complex numbers, and we're not going to go that deep into it, I assure you. But we can plot these complex numbers just like we would do a regular xy point. Now notice a couple differences on my new plane right here is that my x-axis has now become my real axis, and my imaginary axis is what used to be my y-axis. So if I'm wanting to plot the point z equals, let's just make one up, 3 plus 2i. Okay? What that means is that this 3 right here is my imaginary part. So I'm going to go over 3 on my real axis. And then the 2i, well, that's my imaginary part. I'm going to go up 2 on my imaginary. And so these are not going to be lines yet. Okay, we're not quite there yet. These are just going to be points on there. So if I was to do the complex number z equals negative 7 plus 4i. Again, this is going to plot a lot like negative 7, 4. It's going to plot just like it, except for we're just needing to look at it in terms of real and imaginary now. Okay, so 1, 2, 3, 4, 5, 6, 7, negative 7, and 1, 2, 3, positive 4. I'll leave it right there. Okay. Now, I have several that I might assign of this as far as practice goes, and I'm willing to bet you'll see it on your upcoming assessment. Let's see, it'll be a quiz over this. And so what if I was just to give you negative 4i? Well, maybe we should think about rewriting it first. 0 minus 4i, isn't that still negative 4i? Meaning that I'm not going to go left or right on my real axis. I'm just going to drop 1, 2, 3, 4 spots on my imaginary axis. And so this would be the point, not this other one that looks like this. There we go. Trying to make that look simple, not harder than it is, because it really is simple. So I hope that comes across as looking halfway simple. Okay? Because what we want to do in this section, in this video, is I want to be able to take this imaginary number right here, negative 7 plus 4i, and I want to convert it into something called polar form. Polar form. And so I've got some formulas for you. I'm going to try to have the formulas make sense to you, as I normally do. A little spot right there is going to bother me more than it's going to bother you. So suppose I'm just going to make up a random spot right here. Okay, it turned out to be 3 plus 5i. Okay, and so in order to figure out what the x value is, we can use some right triangle trigonometry to get that the x value is r times cosine theta. And our y value is r times sine theta. And then just using Pythagorean theorem, r is going to equal the square root of x squared plus y squared. So you might be thinking, okay, whoa, he's going too fast. Where did all that come from? Well, let me show you. Okay, I'm going to go ahead and form a reference triangle from this. Got a lower right triangle. Probably should have went a little bigger, but hopefully this will work for you. Okay, and again, normally this would land at some random point right here, x, y. What I'm wanting to do is switch it to polar form, okay, where x is how far I went on the real axis, y is how far I went on the imaginary axis, and then my r is going to be, it's called the absolute value. It's the distance from the origin out to this point right here. Okay, so all of this should be a review from our right triangle trigonometry. So now what I'm going to have is z equals, let me use x on this, since that's what I used up there. X plus yi. I'm writing way too big. Okay. Now if I do some substitution on this, I'm going to get that my x is going to be r cosine theta. And then I'm going to move my I up here in front. And then my y, well, it's equal to r sine theta. Making it so that my z is equal to, well, I got a common factor right there. So they like to go ahead and pull that out here in front. R cosine theta plus I sine theta. See this guy right here? That is my polar form of a complex number. It's got that r in there. It's got the theta in there. And so that's what I'm going to be looking for. Okay. Now, r does have a different name. You're going to hear me call it the radius a lot because that's what it is. But the book might call it the modulus. So that will just be another name for r. And you'll hear me call theta either like the, most of the time I guess I'll call it the angle. But it's also called the argument. So I might try to use that a little bit, just a little bit better terms for it. And I don't like this abbreviation, but from the problems I assigned and how easy it is to get those to you on the website with the answers right there involved, they like to use an abbreviation for this whole red box right here. And so the abbreviation they use is they pull this r out right here. They pull the c from the cosine. They pull the I from the imaginary. They pull the s from the sine. And they pull a theta right here. And so it's like the r cis theta. Again, Mr. Lovelady on this, is very sad to see this, and I will not be using this at all. However, this is how they will have some of the answers for you in your practice problems. I love this red box right here. Right? That is my boy. It is good. That's the way I like to see the answer, because there's so much more we can do with this red box when we see everything out. I'm afraid that we'll forget what the C, I, and S stand for and get something backwards. I want to go ahead and see this red box. So good stuff for the note card real quick. All right, all this X, Y, and R stuff is good, and then this box right here, Z equals R times cosine theta plus I sine theta. Okay, those are the important things I want you to see from this. So what I want to do is I want to take some complex numbers and I want to write them using polar coordinates. So let's put this to work in example 2 and express the complex number 4i using polar coordinates. Now, I put a graph out here. You're more than welcome to use a graph to help you solve these. I see that 4i would just be straight up here. I don't have a real part to 4i, so I didn't go anywhere on the real axis, and I just went straight up 4 units for 4i. Okay. Now the big kicker on this is going to be get your hands on the r, get your hands on the theta. Okay. And so remember r, my formula for r was just the square root of x squared plus y squared. Okay. And so where x is going to be my real part, and then y is the coefficient from my imaginary part. And so if I plug this in, that's just going to be, well, my real part, there's not one. It's actually 0 plus 4i, so it's going to be 0 plus 16. Hopefully you would get that distance, that this radius of the circle that would come up to here, or the distance from the center up to the point 4i would just be 4. Okay. But next up, I got to find my theta. So r is equal to 4. Next, I got to find my theta. So I'm wondering how far it opens up from this positive x-axis. Well, we know good and well that's going to be pi over 2. Okay? Anytime I land on a quadrant, that should be easy for me to find. And so I'm ready to write this in polar form. It's kind of weird to say polar coordinates because it makes me think of something else. But I'm ready to write this in polar form. It's going to be my r times cosine pi over 2 plus I sine pi over 2. And so we're always looking at these numbers being the same, and this is just kind of the blanket where you plug stuff in. You plug your r there, and then your theta, plug it in twice here and here. And so that would be my answer. Some people say, well, I want to go ahead and simplify this all the way down. Hold your horses, we're going to get to that. But if I was to actually simplify this all the way down, I would get back to this z equals 4i. Let's do one that does not land on a quadrant angle, on an axis. Okay, I'm wanting the polar form of negative 4 plus 4i. Ooh, I didn't give you a thing on this one, but it would be up here, right? Okay. So, again, I want my r and I want my theta. I got to get my r is just simply going to be the square root of the real squared plus the imaginary squared. Well, that's 16 plus 16 is 32. We are not using decimals. We are using simplified square roots. 32 is 16 times 2, which gives me 4 square roots of 2. That is my r. So look, I could go ahead and start this. Z is going to equal 4 square roots of 2 times cosine theta. Gotta figure out what that theta is going to be. Well, once again, I don't think it's going to be too bad to realize what this angle is. We're used to finding that angle, but let me give you a formula to help me find it. Okay. So what I'm going to do is I'm going to go back to one of those formulas that was in the box a couple times ago, and I had a formula that said x equals r cosine theta. Correct? Remember that x is just this right here. This is x plus yi. And so x is just going to be that negative 4. R, well, that's what I just found. 4 square roots of 2 cosine theta. And so if I divide both sides by 4 square roots of 2, let's see, the 4's cancel. I'm left with cosine theta equals, that'd be what, negative 1 over square root of 2? Rationalized, square root of 2 over 2, negative. So, cosine of what angle gives me negative square root of 2 over 2? You could do a cosine inverse on that. And this is one of my nice values that we're going to have to pick up. And so, negative square root of 2 over 2, let's see, what's that? That's like pi over 4. In the second quadrant, that means that must be coming over 3 pi. And so I can plug that in for my thetas. And this is my answer. Again, I apologize. I really don't like how the book does this. It's going to say 4 square roots of 2 CIS 3 pi over 4, something like that. And this just it's just confusing, I think. And so I really like this answer right here. Okay. Even if you write this down, I'm probably going to go back in your work and find where you did this. So please leave it written out long form, polar form. All right, you got this one. All right, I'm going to let you find the r and the theta, put it in polar form for me, and come back and see if you get the same thing I get. So hit pause on the video. And here's what I got on it. Careful. Make sure this one turned out to be in the first quadrant, positive and then positive 1, right? And so I'm just need to make sure I get that pi over 6 out of the first quadrant. So a little sketch on it doesn't hurt to make sure you're getting the right angle. Because even if you are typing your calculator cosine inverse of square root of 3 over 2, it's got that domain restriction on it. So make sure you're getting it in the right quadrant. It worked out on this one, okay. All right, let's talk about going the other way. So suppose that they give me something that's in polar form. I want to write it back in rectangular form. Rectangular form just means that I want to write it as xy. So wherever this lands, where I have a radius of 12 and I went out pi over 6 units, so a radius of 12 pi over 6 units, I want to know what that xy point would be if I was to transpose the polar form back to an xy axis. Well, the book goes into pretty good detail on this, but I'm going to make it so it's pretty easy for us. Okay, so rectangular form. Let me rephrase this. It is that xy, but remember I do want it as a complex number, so I'm going to want my answer as x plus yi. I think at the beginning of the video I called it a plus bi because that's what we did in Algebra 2. We're going to kind of go to this x plus yi form. And so my goal on this is just going to be to do what some of you might have had intuition to do earlier, is just simplify everything. If I was to take cosine of pi over 6, well, I just did that. I got square root of 3 over 2 plus I. If I was to take sine of pi over 6, that gives me 1/2. Man, those pop quizzes that we got in the third quarter, that information is not going away. And so if I distribute this 12 through now, I get, let's see, 12 divided by 2 is 6 square root of 3 plus 6i. I like going polar to rectangular a lot better than I do going to from rectangular to polar. I assure you, you'll see it both ways. Go again, just in case you have a question on it, all right? This time, I'm not going to give you the polar form. I'm just going to tell you about the polar form. Okay? It has a radius, or a modulus, as they call it, of 13, and it tells me that tangent theta equals 5 over 12. Now that tells me a lot right there. Tangent theta equals 5 over 12. I can actually draw me a triangle and figure out everything that's going on with this. Okay, so I want to get this into polar form first, because they weren't even nice enough to give me a polar form on this. So my radius goes on the outside. Cosine of this theta right here. Well, cosine of that theta is going to be adjacent over the hypotenuse, so 12 thirteenths. Oops. Let me just do this first. Okay, so that was actually my r. So now I'm going to plug everything in. So cosine of theta we said was 12 thirteenths. Plus I sine of theta, I'm going to need to go opposite this time. Opposite over hypotenuse, 5 thirteenths. Distribute the 13. What happens? Get this nice complex number, and that's what z is. Your turn. Pause the video, give this a go, and then come back and see if we match up. Not just a whole lot of work on these. Okay, careful. I did throw your curveball and threw a negative in right here. I think you guys can handle that though. Okay, practice this. Right? And then the next video we'll be doing some operations with these complex numbers in their various forms.